we're going to learn how to solve a first-order differential equation using an integrating factor. We start with the first-order differential equation, which can be written in general in this form. Some function p of t times y prime plus q of t times y equals g of t. Here's an example. T squared y prime plus 2t times y equals 6. A straightforward first-order linear differential equation. How are we going to solve this differential equation? Well, we're going to notice that this left side here is just the derivative with respect to t of the product t squared times y. That's just using the product rule, t squared y prime plus 2t times y. Because of that, we can just integrate both sides of this equation very easily. When we integrate the left side, we get t squared times y plus some arbitrary constant. When we integrate the right side, we get the integral of 6 dt, which is 6t plus an arbitrary constant. We can put the arbitrary constants from both sides over to the right side. We'll call it c. And then we just solve for y, dividing both sides by t squared. We get y equals 6 over t plus a constant over t squared. All of this comes from the product rule for differentiation, which we're running backwards here in the first step. Because of the product rule, we like to see a form like this appearing in our differential equation, so we'll call that form exact. And this is a special case of what we'll see later in the book. It gets called exact. Can we use this method to solve general differential equations? Well, we start by writing the differential equation in this somewhat reduced form. Remember, any first-order linear differential equation can be written as p of t times y prime plus q of t times y equals g of t. If we just divide through by capital P of t, we get y prime. Cross that out. We get y prime plus q of t over p of t, y equals g of t over p of t. And we'll just call this part here the capital Q of t over capital P of t. We'll call that little p of t. And on the right side, we'll call this little g of t. So we can put any first-order differential equation in this form as long as our p of t is not identically 0. If it were identically 0, then, of course, it wouldn't be a first-order differential equation. Here's our idea for a general method of solving a first-order linear differential equation. We first put it in this standard form. We ask, is there some function mu of t, which we're going to call an integrating factor, which when we multiply it through by the equation gives us this left side here. Is this going to be exact? If it is, we can integrate both sides. Well, what does it mean for this to be exact? It means that this looks like some function f of t times y prime plus f prime of t times y. Is there a function f that makes this work? Well, in order for this, let me write this again here. In order for this to be of the form f of t y prime plus f prime of t y, we need mu of t to be our f of t and mu prime of t to be mu of t times p of t. because mu prime is just f prime. And that's what's over here on the right, which has to match it, that term there. So here's the question. This is the equation I wrote before. How can we find a function mu that has mu prime of t equals p of t times mu of t? We're going to talk about solving differential equations like this shortly, the general way, but this is a simple enough one that we can just write down a solution and check that it works. I claim mu of t equals e to the integral of p of t dt works as a solution. Can we check that? Let me check that here. How do we check that? Well, for this function mu of t, what is mu prime of t? Well, we just use the chain rule to differentiate. It will be e to the integral of p of t dt times the derivative of the integral of p of t dt. But of course, that derivative is just p of t itself, and this just gives us p of t times e to the integral of p of t dt, which is p of t times mu of t. And so it's very easy to check that this is a solution to this differential equation. Now, when I say a solution, notice that here, when we write mu of t equals e to the integral of p of t dt, there's an arbitrary constant that will be associated with this integral. The claim is it doesn't matter what that constant is. You can pick any representative of this indefinite integral, any antiderivative of little p of t, and use that here, and you'll get a function mu that satisfies this differential equation. The fact that there are many different ones, and they all differ from each other by having an additive constant here in the exponent, means that the different functions mu that satisfy this differential equation actually differ by a multiplicative constant, and we'll see that won't matter when you multiply them through this equation. If you just used one solution mu here, one integrating factor mu of this form, if you used 2 mu or 17 mu, it would just put an extra factor of 17 on both sides or 2 on both sides, and that wouldn't make any difference at all for what we're going to do. I already talked about that. Okay, how do we make use of that? So we start with the differential equation of this form. We multiply both sides by our integrating factor. Remember, our integrating factor here will be mu is e to the integral of p of t dt. We recognize this now as exact. So we can integrate both sides. When we integrate the left side, we get mu of t times y. When we integrate the right side, we get whatever that integral is. And then to solve for y, we just divide by mu of t, and we get our general solution of this form. Note, in this general solution now, there is an arbitrary constant associated with this integral, which we can't lose, otherwise we won't have all of our solutions. As an example, let's solve this first order linear differential equation. What is the integrating factor here? Here we'll use mu of t is e to the integral of p of t. Our p is just 2 dt. Of course, the integral of 2 dt is just 2t. Remember, we could add a constant there, but it won't matter. So we'll just use e to the 2t. We multiply through our original equation here becomes, multiplying through by the integrating factor, e to the 2t y prime plus 2 e to the 2t y equals, multiplying through by e to the 2t, we get 9 e to the 3t. Now we integrate both sides, and we see the integral of the left side is exactly e to the 2t times y. The integral of the right side is now just 3 e to the 3t plus a constant c. We put that constant from integrating both sides over here on the right. We then divide by e to the 2t to solve for y. Y equals 3. E to the 3t divided by e to the 2t, which is e to the t, plus, don't forget this part, c over e to the 2t, which we could also write as 3 e to the t plus c e to the minus 2t if we wanted to do that. So now we have our general solution to the differential equation. Always check your solutions. Y equals 3 e to the t plus a constant times e to the minus 2t. We can compute easily y prime is 3 e to the t minus 2c e to the minus 2t. And then you check y plus 2y is just y prime plus 2y is y prime plus 2 times y, and that's 9 e to the t, which matches our original differential equation right here. That tells us for any constant c, we get a valid solution.